Welcome to Factorising Quadratics. Now you're thinking, yeah, I know everything I need to know about quadratics, and I'm thinking, well, why did you follow the link then? When am I ever going to be factorising quadratics? Funny thing you should ask that, because just the other day I was in a room full of people and they were depending on me to factorise some quadratics on the whiteboard in a lesson. Yeah, okay, fair enough. You might never use it again, but let's hope that what I'm going to go through here is useful to you, in the short term at least. We have a general quadratic, ax squared, add bx, add c. Now if it's equal to naught, it's an equation. If it's not equal to naught, it's an expression. And either way, the way you progress through the question is to factorize. So what we're trying to do is turn this into a couple of factors, hence the name factorizing, equal to naught, because we know if two things multiply to make 0, then either p equals 0 or q equals 0, and that leads to a simpler problem to solve rather than just putting different values of x into this initial equation hoping to get 0 out. So let's summarize what you've probably already been told up to this point. It will usually apply to expressions where you've only got one lot of x squared. Your quadratic will be in a standard format, ax squared plus bx plus c. A, b and c will be numbers, and most of the time the coefficient of x squared is 1. And you will have been told, or you are working through at the moment, the fact that the two numbers in the brackets, when you factorize, have to multiply to make c and add up to b. And then it's just a matter of working out your factor pairs, taking positive and negative signs into account. Now I want to pick up that idea, and we'll start with something simple like x squared add 7x add 12 equal to 0. And I want us to just look at it in a slightly different way, because what I'm going to do is extend the method you're familiar with to deal with situations where you've got more than one x squared. And it might seem like a different method, but it is actually a more general method compared to what you already know. So I'm going to go through an example you're familiar with, approach it in a slightly different way, and then you'll see that when I extend the method it is really just the same thing but more generalized. So the way we would approach this, we would say we're looking for two numbers that multiply to make 12 and add up to 7. Well, the numbers we're looking for are 3 and 4. So this is where it probably digresses from where you would normally deal with it. I'm going to split the 7x term up into those two numbers, keeping the x's and leaving the rest as it is. Now what I'm going to do is I'm going to factorize each pair of terms separately. So these two terms have an x in common, and I've lost the squared. There we go. And these two terms have a 4 in common. So what I've done is factorize each pair of terms, and I could have had x squared plus 4x and 3x plus 12. Now look here, this factorized expression and this factorized expression have the x plus 3 in common, so it will factorize again. X plus 3 is the common factor of those two parts, and what we've got left is x plus 4. Now that's the result you would probably have jumped straight to. X squared plus 7x plus 12, 3 and 4 in the brackets. So I've introduced these two steps that at this stage you don't really need because it's a simple problem. What I'm going to do is extend this idea for more general terms. So here's another example. 2x squared, take away 9x add 4 equals 0. You'll notice I didn't solve that quadratic equation. All I'm interested in at the moment is the factorizing aspect. The answers that follow from it are fairly routine. Now, let's have a look at this. Now, I can't say I want two numbers that multiply to make 4 and add up to -9, because one of your brackets is going to have a 2x in it, which messes up the pattern. So this is where it's slightly different to what you're familiar with. What I want to do is I want to look for factors of 2 multiplied by 4. So I want factors of 8 that add up to -9. Now it might seem a different method, but when this is a 1, you are actually finding factors of 1 times by. So let's just go back up to this previous example. Where we've said factors of 12, it is actually 1 times by 12. So it's the same method, but we don't often introduce this 1 and put in these 2 steps here. Back to the problem at hand then. I want factors of 8 that add up to -9. Now the numbers I'm looking for are -1 and -8, and as in the example above, I split this up into those 2 terms. So I get 2x squared, take away x, take away 8x, add 4 equals 0. I now factorize this pair and I factorize this pair. These two have an x in common. That gives me 2 take away 2x, take away 1. And I factorize this pair into -4 lots of 2x, take away 1. Now you might say, why have I taken a factor of -4 out? A little bit more familiarity with this method will remind you that the factor you're looking for is this one. So because I've got a -8x, I need to subtract. I need to take a factor of -4 out so that it gives me a positive term in that bracket. That just comes with practice, as with a lot of maths. Now I can see that the 2x take away 1 is the factor that these two expressions have in common, and leaves me with the x take away 4 in the other. And then the next step follows, that x is 4 or x is a half, but I'm not really focusing on that bit at the moment. Let's try a different example. 3x squared, take away 5x, take away 2 equals 0. Again, multiply these 2 terms together. In the general quadratic it's the a and the c. So I want factors of -6 this time that add to -5. Now the 2 numbers that multiply to make -6 that add up to 5 have got to be -6 and +1. They have to multiply to make a negative, so they have to be different signs. Add up to a negative, so the bigger one must be the negative one. Same reasoning as for any quadratic that you're used to factorizing. Factorizing in pairs, these have a factor of 3x in common. That gives me x take away 2, and I can see the x take away 2 is there, so I input 1 lot of, just so that I can see that bracketed term repeating. So x take away 2 is one factor, 3x add 1 is the other. Now with all of these you could do it by trial and error. You know that 3 is prime, so one of the brackets has got to have a 3x in it. 2 is prime, so one of the brackets has got to have a 2. So in some situations you haven't got that many options to try if you just want to do it by a bit of trial and improvement. Where it becomes a little bit more problematic is if this is something like a 12, then you've got lots of different factors to try, and again if this isn't a prime number at the front. We're just trying to make it more efficient so that you're not having to spend an awful lot of time trying different possibilities. Another example. Six x squared plus 7x take away 3 equals 0. So I want factors of minus 18 that add up to 7. So again, the numbers have got to be positive and negative, and the larger one has got to be the positive one this time. So the numbers I'm looking for are plus 9 and minus 2. Factorising pairs, these have got a 3x in common, so that gives me 2x plus 3. Because 2x plus 3 is the common term, and you can see these are both negative, I take out a factor of minus 1. (2x plus 3) is the common factor of those two expressions, leaving 3x take away 1 as the other. And there we go. Let's generalize. To factorize, we're looking for factors of AC which add up to B. Call these alpha and beta. We then write Bx as alpha x plus beta x, and factorize the 4 terms in pairs. Let's try another example. As with some maths, it's easy to do an example to illustrate a method than it is to try and generalize, because the generalization gets an awful lot of fiddly notation in it. So 6x squared, add 17x, add 7. So I want factors of 42 which add to 17. 14 and 3 are the two numbers I'm looking for. So 6x squared, add 14x, add 3x, add 7. Factorize in pairs. This is 2 lots of x, 3x plus 7, and 1 lot of 3x adds 7. So this factorizes into 3x adds 7, 2x add 1. You might have said by now, well, what if those middle two terms were written the other way around? Well, let's have a look here now. I haven't done it with them all. I wanted you to get the method sorted before I started overcomplicating it. So let's just write it the other way around. It can only be those two factors, but what might differ is the order that you write them down. Let's factorize this pair. You can see a 3x they have in common, so that's 2x add 1. These two have a 7 in common, which leads to 2x add 1. So all that means is the way that you pair them up has altered, but they are effectively the same, aren't they? We know this. If you want more practice at this, then look in some of the textbooks that deal with A-star material. You can look at My Maths and go for the A-star section, the boosters. Another website that's useful is Waldo Maths. this also has a visual aspect to it, so let me find it. Here we go, here's that very example we've just done. Right, this is more of a trial and improvement sort of method. You can see here the way it allows you to use sliders to change things. We've already worked out the answer for this, so if we're going to take this as being 2x add 1, then a is 2. Let me get it working. And b is 1. You can see that this is building it up as it goes. C was 3 and D was 7. So this is a more trial and improvement method to help you to see the two factors that you're looking for, or the two bits that you're going to split the x term up into. Choosing easier problems, well, that doesn't look a lot easier, does it? But experiment with it if you want something to produce lots of results to try out. Okay, so I hope that's been useful. Happy factorizing. Remember, you never know when you might need to put things in brackets. Take care out there.